Hello and welcome to today's session. Today we will be discussing one of the topics called lapse rate and atmospheric stability for the CUET Geography Examination 2023. So without wasting a minute, let's start with the session. So my name is Harsh and I am a teacher of geography at EXAMVAT. I have qualified NET JRF in my first attempt and I have pursued geography learning in my college education. So that was all about me. Well, let's start this session with a question. Have you ever wondered why Gangtok and Delhi, though both located on same latitude, experiences completely different climate? While Delhi experiences extreme temperatures, Gangtok has a relatively moderate temperature. It is experiences a cool climate. Well, that is because Gangtok is situated on higher elevation in comparison to Delhi. So what we get from this is that as the elevation increases in lower atmosphere, the temperature is bound to decrease. This change in temperature with increase in altitude in the lower portion of atmosphere is called normal lapse rate, where we see temperature decreasing at the rate of 6.5 degrees Celsius per kilometers, which is called as normal lapse rate. But under some conditions, what we will also experience that the lower portion of the Earth atmosphere, the one around the Earth's surface, will be relatively warmer in comparison to the air above. Well, that is because of terrestrial heating, and under such conditions, what we call is inversion of temperature or negative lapse rate. So, why is it that the lower portion of the Earth's atmosphere is relatively warmer, whereas as we move above, the atmosphere tends to cool down? Well, there are two significant reasons, and if you have studied the composition and structure of the atmosphere, you would be knowing that. The first one is that most of the heating of the atmosphere is by terrestrial radiation, which Earth emits. So, as distance from the Earth increases, the distance of atmosphere from the heat source increases. So, the atmosphere's distance from increasing heat source results in lower heating, which we experience in the form of reducing temperature. The second point is that the main constituents which absorb heat of the atmosphere, carbon dioxide, atmospheric water vapor, and dust particles, they are all concentrated in the lower portion of the atmosphere. If you remember, we must have taught you that the 10-kilometer boundary of troposphere, which we see usually as average height of the troposphere. So in that zone, we believe atmospheric water vapor and dust particle exist. But the dust particles and atmospheric water vapor are concentrated in just 3 kilometers of the atmosphere. So the absorbance concentration is decreasing as height increases, which is resulting in lesser and lesser absorption of heat with increasing height, resulting in lower temperatures. Now, what are the types of lapse rate? You have studied now that the temperature of the Earth decreases with increase in altitude, and that is because of lapse rate. Now, there are few types of lapse rate that you need to remember. So, the generally we have studied up till now was normal lapse rate. What is normal lapse rate? The addition or subtraction of heat to the parcel of air resulting in its cooling or warming will be called normal lapse rate. Okay, but there is other type of lapse rate where the rate of cooling and heating changes in response to change in pressure and volume condition of the atmosphere. Okay, so the parcel of air will not be moving, will not be heated, but it would expand, and that would result in heating or cooling of the atmosphere. So it will, if it will be expanding, it will cool, and if it will be contracting, it will be heated. So this type of condition is called adiabatic heating and cooling, and the lapse rate as a result of adiabatic heating or cooling will be called as adiabatic lapse rate. Okay, so the adiabatic cooling differs in actual atmospheric condition due to addition and removal of latent heat. Latent is an heat is an important factor which determines the rate of cooling. The other type of lapse rate is environmental lapse rate. It is nothing but the actual rate of temperature change in the atmosphere with the change in altitude at any given point of time. Okay? So when I say there is a 6.5 degrees Celsius decrease in temperature with increase in height, it is a normal condition, but this condition differs. So at this point of time, maybe it is too warm here, okay, too warm in Delhi, suppose, and the temperature change is very rapid. So it is decreasing at a rate of 8 degrees Celsius per 1000 meter or 6 degrees Celsius, suppose it is cooler period of time. So that would be termed as environmental lapse. It is nothing but the actual change in temperature of the atmosphere with the change in altitude at any given point of time. Okay. So that will be called as environmental lapse rate. Now, what is latent heat? You have understood that latent heat is responsible for adiabatic heating and cooling. But what is latent heat? Latent is derived from the Latin term, which means hidden. So latent heat is an hidden form of heat. What happens is that when matter is undergoing change, or suppose in this case water. So when water is changing from solid to liquid state or liquid to gaseous state, there is a hidden form of heat which is transmitted when it undergoes a change in state. Okay, so this hidden heat will be called latent heat. Latent heat is just understood as an energy in hidden form which is supplied or extracted to change the state of a substance without changing its temperature. This is an additional heat, which latent heat cannot be measured by normal thermometers. Okay, do remember that. So latent heat of evaporation. What is latent heat of evaporation? When a substance is undergoing water vapor, suppose water vapor is undergoing change from solid to liquid, then a heat will be released which is called as latent heat of evaporation. When water is converted into liquid form, or when liquid form of water is converted into gaseous form, a latent heat which is associated with the process is called latent heat of evaporation. Now there is second form of latent heat called latent heat of condensation. So what is this latent heat of condensation? It is the process in which the gaseous part is changes into liquid part. It is condensing. Okay, the gaseous matter is condensing into liquid part. So that will be called latent heat of condensation. So evaporation is a cooling process because latent heat is absorbed, whereas latent heat of condensation is a heating process because in the process heating is released. So wherever latent heat of evaporation will be found, what you will see is that there would be cooling of the surface. But wherever latent heat of condensation would be seen, there would be warming of the surface. So remember these 2 points very carefully because this is the whole concept on which we will be now studying dry and moist adiabatic lapse rates. Okay, so adiabatic heating and cooling. Now we have understood what is lapse rate. Okay, now let's jump to adiabatic heating and cooling. Okay, so the change in temperature of moving parcel of air without addition or subtraction of heat. There will be no addition or subtraction of the heat in the moving parcel of air. The volume of heat which it's contained will remain the same, but it would be there would be change in temperature because of expansion and contraction of mass or volume of the parcel of air. Okay, so when I say expansion and contraction, I mean that air will expand, okay, and the expansion process will result in heating, and contraction process will result in cooling of the moist air. Okay, so the first type of lapse rate, adiabatic lapse rate, is called dry adiabatic lapse rate. Okay, so what happens? Dry means the air is dry. There is very little relative humidity, or the relative humidity is really less to disturb the process of ascent of air, to disturb the process of rising of warm air. Okay, the humidity is relatively really less. So that is called dry adiabatic lapse rate. So under the dry adiabatic lapse rate, a rising air is cooled at a rate of 10 degrees Celsius per 1000 meter. Okay, so a rising air mass will be uh, cooled at a rate of 10 degrees Celsius, which is called as dry adiabatic lapse rate. So how does air rises? So see this photograph here. What will happen is air is heated on the surface. Okay, if there is surface overheating, so the air in contact with the surface will also be getting heated. So on heating, it will expand. On expansion, it will become lighter than the surrounding parcel of air. When it will become lighter, it will rise upward, and on rising upward, it will cool at a dry adiabatic lapse rate of 10 degrees Celsius per 1000 meter. Okay, so if you see here, the surface temperature is 30 degrees Celsius, and after 1 kilometer, it has become 20 degrees Celsius, and after another kilometer, it has become 10 degrees Celsius. So this is what lapse rate is about. Okay, expansion of air resulting in its uplift because it becomes relatively lighter and cools down. Now suppose a dry air is descending, then what will happen? So a descending dry air will cool at a rate of 10 degrees Celsius per 1000 meter. Okay, and that so it will become relatively warmer and warmer because it is descending, so the atmospheric pressure is increasing. It will get compressed, and the temperature will increase. So that is called dry adiabatic lapse rate. Now the dry adiabatic lapse rate is usually associated precipitation on the leeward and windward side of the mountains. Okay, but before explaining that, let me tell you what is moist adiabatic lapse rate. Okay, so Moist adiabatic lapse rate is also called retarded adiabatic lapse rate, and this is so because the rate of cooling in moist adiabatic lapse rate is lesser. The air cools at a rate of 5 degrees Celsius per 1000 meter when it is ascending. Okay, and the moist adiabatic lapse rate or the moist adiabatic condensation takes place after the condensation height is reached. So you see this photograph here. So what happens is the air is relatively dry and it is ascending. Okay, on ascending it is getting cooler. So when it reaches the condensation level, so what is condensation level? Condensation level is that height beyond which the water vapor converges and it converts into liquid form. Okay, so as it is rising upward, it is cooling. So on cooling, the relative humidity is increasing, and when the relative humidity reaches to the level where it can convert in liquid form, that will be considered as a condensation level height. So beyond this height, the air will rise and will cool at a retarded adiabatic lapse rate or wet adiabatic lapse rate of 5 degrees Celsius per 1000 meter. Okay, so you see 32 to 22, 22 to 12, 12 to 2 degree. There is a change of 10 degrees Celsius. Air is getting cooler at a rate of 10 degrees Celsius. But here, after reaching the condensation level, the air is cooling at a rate of 5 degrees Celsius per 1000 meter. So it changes from 2 degrees Celsius to minus 3 and minus 3 to minus 8 degrees Celsius. So this is how wet adiabatic lapse rate functions. And why the rate of cooling in wet adiabatic lapse rate is slow? Because when the water vapor reaches condensation level, it changes into liquid form, and the latent heat which it was carrying during after evaporating, the latent heat which it was carrying, it is released in the atmosphere, resulting into warming of the atmosphere. Okay, so thereafter the rate of cooling decreases due to release of latent heat. So that latent heat is called latent heat of condensation. Thereafter, the rate of cooling will decrease at a rate of 5 degrees Celsius per 1000 meter. So these are the two important points you need to remember about moist adiabatic lapse rate. So there is a special class of moist adiabatic lapse rate called saturated adiabatic lapse rate. What is this lapse rate? When the relative humidity is at 100%. Okay, that is called saturated adiabatic lapse rate within moist adiabatic lapse rate, and it varies with temperature of parcel of air. Okay, now imagine if the initial temperature of the rising air is relatively higher. So imagine if this temperature was 52 degrees Celsius. So what would have happened? The air would have risen to great height. Okay. And if its temperature is 32 degrees, 52 degrees Celsius, it would have a relatively more water holding capacity in relation to the mass of air at 32 degrees Celsius. Okay. So when it will rise, it will carry more amount of latent heat within it because its moisture holding capacity is higher. So the rate of cooling will be slower if the initial temperature is relatively higher after condensation level. Okay, so while I was telling you about the effect of dry and moist adiabatic lapse rate on windward and leeward side of the mountain, so let me just draw a mountain here. Okay, so suppose rain bearing clouds, okay, they are moving from this side, they will come across this mountain, they will rise and they will cool at the rate of 10 degrees Celsius per 1000 kilometers, and thereafter they will form clouds here and there would be rainfall. Okay, but then what will happen? The air will cross this range, its relative humidity will decrease. So now dry adiabatic lapse rate will operate when it descends to this side and the air would be warmed at 10 degrees Celsius per 1000 meter. Okay, descending air will be warmed at 10 degrees Celsius per 1000 meter, and because of which this part, the leeward part of the mountain, will remain dry or barren. So when you read about local winds like Chinook and Fohn, they are all blowing down the slope and are warmed at a rate of 10 degrees Celsius per 1000 meter. Okay, so that is a category of katabatic and anabatic wind, which I will tell you in another video what are katabatic and anabatic wind. But the downslope moving wind will be warmed. So Chinook and Fohn, they are example of winds moving downslope. Okay. Now lapse rate and atmospheric stability. So how does lapse rate affect atmospheric stability? So if the lapse rate would be higher, what would happen is the air will rise at a higher level and lead to instability. Okay, and if the lapse rate will be lower, the air will not rise at a greater speed. That will lead to stability condition in the atmosphere. So if you know that the rate of change of temperature per 1000 meter in the atmosphere, you can draw the environmental lapse rate, graph of environmental lapse rate. But there are two more type of lapse rate that you need to see here. This one shows super adiabatic lapse rate. This one shows super adiabatic lapse rate, and this one shows sub adiabatic lapse rate, and this one shows stability condition. So the x-axis shows temperature and the y-axis shows height. So with increase in height, we see that the rate of change in temperature under super adiabatic lapse rate is relatively higher. So temperature falls down very steeply on achieving little height only. On lesser height also, we see a great fall in temperature, super adiabatic lapse rate. So that is what super adiabatic lapse rate is, when there is a rapid change in decline in temperature with increase in height. Okay, and this one shows sub adiabatic lapse rate, where there is slower change in temperature or slower cooling with increase in height. So this graph shows sub-adiabatic lapse rate, and this one shows stability condition, where there is very little change in temperature. Even though it has reached great height, the temperature here is more around constant. So always remember that the environmental lapse rate will be between super adiabatic and sub-adiabatic lapse rate, while the graph of stability will be almost perpendicular or a straight line. Okay, so environmental lapse rate will be between sub-adiabatic and super adiabatic lapse rates. Now atmospheric stability. So temperature gradient will determine the atmospheric stability. If the, as I've already told you, if the rate of cooling will be higher, okay, so the temperature gradient will be higher and air will be unstable. Whereas if the gradient is low, there would be a stable atmospheric condition. So when there will be stability, what would be the condition of atmosphere? So the rising parcel of air would have a temperature which would be lower than the surrounding atmosphere. Okay, so what it means, sorry, let me repeat myself. I said it wrongly. The rising parcel of air would have a temperature which will be greater than the surrounding atmosphere. So if it is having a parcel of air is having a temperature which is greater than the surrounding atmosphere, it will force it to rise upward, because on rising upward, it will cool. So instability conditions would be prolonged. Okay. And instability condition arises when the environmental lapse rate is less than the normal lapse rate. Or what this statement here means is that the rate at which the rising air is cooling presently is much lesser than the rate in which atmosphere generally cools. Okay, so which means if it is cooling slowly, it is warmer than the surrounding atmosphere and it has to rise upward. Okay, so these two are the conditions of instability in the atmosphere. And what does instability promotes? It promotes cloud formation, because if the air is rising upward, it will form clouds and it would be helpful for rainfall. Whereas instability condition, what would happen is the temperature of the air would be less than or equal to the surrounding air mass. So the atmospheric temperature and the temperature of air would be almost equal, which will restrict the air to move upward, leading into stability condition. So that arises when the environmental lapse rate is greater than or equal to the normal lapse rate. So in that case, the body of air would be cooling at a rate which will be greater than the surrounding atmosphere, resulting in stability conditions. Okay, so stability leads to dry atmospheric condition. That is the con of stability atmospheric condition. Okay, so what we see in Thar Desert or along all the western part of the continent where there are deserts, there is stability condition which restricts upward movement of air, resulting in dry atmospheric conditions. So now that was all you needed to know about stability and lapse rate. Now I have brought some of the previous year questions from the examinations for us to practice. So let's start with them. So the first question, evaporation is sometimes called as cooling process because, well, those who know can write the answers in the comment section. The first option is latent heat of vaporization decreases. Water temperature usually decreases after vaporization. Water temperature usually increases after vaporization, or latent heat is released. So evaporation is called cooling process because of just one thing, that the water temperature will decrease after there would be vaporization. Okay, so that is why water evaporation will be known as cooling process. Now the second question, the normal lapse rate of the atmosphere is, so see here, this was a tricky question and it was cancelled by the board when the final ICT was released, because you see 6.5 degrees Celsius per 1000 meter, 10 degrees Celsius per 1000 meter, 1 degree Celsius for every 165 meters, and 5 degrees Celsius for 1000 meter. Which one of the following is normal lapse rate of the atmosphere? So if you see properly, 1 degree Celsius per 165 meter and 6.5 degrees Celsius per 1000 meter. These both are normal lapse rate. Okay, so any of the two option is correct here. The third question, weather monitoring station in western Rajasthan recorded a maximum temperature of 41 degrees Celsius. Okay, during summer months. What will be the temperature at 11-kilometer altitude? So you are given three conditions here. The first one is maximum temperature on surface, which is 41 degrees Celsius. The second is it is of summer months. So summer months mean their relative humidity will be relatively lesser. Okay, and it is in Rajasthan. So of course relative humidity would be very less during summer months. And what this question asks from you is to calculate the temperature at height of 11-kilometer altitude. Now, if you start calculating at a rate, dry adiabatic lapse rate, so you will see is that the air at the height of 110, 11 kilometers. So if the air is cooling at a rate of 10 degrees Celsius per 1000 meter, it will cool to 110 degrees Celsius at the height of 11 kilometers. Okay. Now you subtract that 110 degrees Celsius from 41 degrees Celsius. So what you will get is 59 degrees Celsius, minus 59 degrees Celsius. So that minus 59 degrees Celsius is not in the option, but the closest one is 58 degrees Celsius. So the right answer would be here 58 degrees Celsius. So this was a tricky question. So you need to be careful in questions like this. Fourth question. A place A and place B are located on same latitude, but place A experiences a lower average temperature than place B. Place A is located in mountainous area. Can you guess the factor responsible for the same? Okay. The options given here are place A experiences lower temperature due to lapse rate. Second option is place A lies on windward side of a mountain range. Option C, both 1 and 2. Option D, neither 1 nor 2. Since you have to make a guess here in this question, so it can be both the factors. First of all, it is in mountainous area, so it will experience lower temperature due to lapse rate. Okay, and the second option is also correct because it may be on the windward side of the mountain, due to which it will receive plenty of rainfall and therefore it will remain relatively cooler. So in this case, option C would be correct. Well, that was all in today's session, and for more useful videos like this, you can follow our channel EXAMVAT. Thank you so much.